Welcome to our instructional video on preparing and upgrading the S4HPS device system for posterior segment procedures. At the beginning, we present you an overview of the equipment required for this as well as the specific device accessories. The device system Megatron S4HPS, the laser system Endotron 532 as a photocoagulation system and the endoillumination source Xenotron 3 are arranged one above the other on the equipment trolley. Below the touchscreen of the Megatron S4HPS are the connection sockets intended for connecting the device accessories. Port 1 serves to connect the filter of the air injection system with a pre-connected three-way valve. The blue compressed air connector of the pneumatic vitrector is to be connected to port 2. Finally, the oil injection system is to be connected to port 4 via a bayonet lock. In contrast to surgical interventions in the anterior segment of the eye, the brightness of the touchscreen is greatly dimmed. In the generally darkened operating room, the surgeon should not be hindered by ambient light. The display of the vitrectomy module with target and actual parameters of the cutting rate of the vitrector, specified in cuts per minute or CPM, is located on the left of the surgery screen. It should be noted here that when using a Mach 2 cutter, the currently displayed cutting rate must be multiplied by a factor of 2, since this type of vitrector has 2 cutting edges. Next to it are the displays for the aspiration, vacuum and flow modules, the functions of which you are already familiar with from our course on anterior segment surgery. The type of pump to be used, peristaltic or Venturi pump, can also be selected here. The diathermy and air modules are also active. The air function should always be switched on during interventions in the posterior segment of the eye. The medium to be introduced into the eye, BSS or air, must be selected by the user via the orientation of the three-way valve. The equipment accessories for performing rear segment interventions are now arranged on the instrument table. We start with a general overview first. This is followed by a separate presentation of the individual accessories. Initially, the trocar set, which consists of 3 trocar lances and an injection holder. The need for 3 trocar lances in the set will be explained later in this video. The next accessory is the vitrector, which, in conjunction with the S4HPS device system, implements the actual removal of the vitreous body. The air injection set with air filter and pre-connected three-way valve, this can be used to select the medium required for introduction into the eye. The oil injection system, consisting of a plastic cartridge and hose system with device connector, is used to inject silicone oils. The overview is completed with the laser fiber for use with the Endotron 532 and the light guide for operation with the Xenotron 3 or the LED light source Solia. Let's start the presentation of the individual accessories with the trocar set. Trocars are used to gain access to the posterior segment of the eye. They have a valve function so that no medium can escape even if there is no instrument in the trocar port, so the characteristics of a closed system are retained at all times. The trocars are positioned in the area of the pars plana, a structural section of the non-seeing retina that lies between its outer edge and the ciliary body and contains neither larger vessels nor fundamentally important functional tissue. The pars plana is about 3.5 to 4 mm away from the limbus. Measuring marks on the proximal end of the trocar lance are used to mark the position of the trocar ports. The trocar set includes 3 trocar lances, as 3 approaches to the eye are required as standard. A first access serves to accommodate a light guide for endoillumination, the illumination of the inside of the eye. A second access is intended for the respective working instrument. Initially, the pneumatic vitrector will be used here. Finally, a third trocar port is provided for connecting the injection holder contained in the trocar set. The injection holder conveys the desired medium, here BSS or air. The required medium is selected via the position of the three-way valve and can be adapted to the surgical situation intraoperatively. Using an artificial eye as an example, the insertion of the trocars will now be demonstrated. Right next to the trocar set with injection holder, the three-way valve of the air injection set can already be seen. The measurement markings on the trocar lance are used to locate the position of the sclerotomy appropriately and to ensure correct insertion of the trocars into the pars plana. The introduction of the trocar lance is initially carried out at an angle of 5 degrees until about half of the scara thickness is reached. The lance is then raised to about 30 degrees to the scara and the sclerotomy is finalized. The trocar port is secured with forceps and the lance removed. This technique of insertion is intended to ensure that the trocar lances follow the lamellar structure of the scara and result in only a small wound channel with correspondingly little trauma. The created sclerotomy should be self-sealing after removal of the trocar and thus make suturing over the sclerotomy superfluous in most cases. The hose of the air injection system is equipped with a permanently attached air filter, which is to be connected to socket 1 of the S4HPS system and enables the provision of microfiltered air for entry into the eye. At the opposite end of the hose, there is a pre-connected three-way valve to which the injection holder of the trocar set and the infusion line coming from the cassette of the device system are connected. The long leg of the three-way valve is marked off and thus shows which supply line is currently closed. Depending on the position of the limb, either saline solution or filtered air is infused into the eye. After the trocars have been inserted, the injection holder included in the set must be connected to the three-way valve using a luer lock. Here, the correct setting of the three-way valve must be observed in order to ensure the delivery of the required medium. The air filter of the air injection system is then connected to socket 1 of the device system, the designation of which is illuminated when the corresponding surgery step is called up. Finally, the infusion line is connected to the unoccupied connection of the three-way valve. The infusion solution is fed from the infusion bottle via the cassette of the device system into the eye. BSS and microfiltered air are now available. The injection holder can now be inserted into the trocar port with the help of a forceps. For surgical intervention in the posterior segment of the eye, the use of a light source for endoillumination is necessary. In general, the dimensions of the accessories should be coordinated. In this case, 25-gauge trocars and 25-gauge light fibers are used. The light fiber connector must always be fully inserted into the connection socket of the light source in order to achieve proper light output. Here we use our xenon light source, the Xenotron 3. The portfolio of GEUDER also includes the new RGB light source Solia, which uses LEDs to provide the necessary intraocular illumination. The light fiber is now connected to the Xenotron 3. The size and design of the light fiber can be entered via the GUI, where red stands for 20 gauge, green for 23 gauge and blue for 25 gauge. The light fibers can be designed as spot, wide angle and shielded wide angle. After selecting the respective light fiber used, the desired light intensity must be set. The activation button is located at the bottom of the display. In the standby mode, an aperture is placed in front of it so that not the full amount of the selected light output is emitted. When activated, this aperture is removed and the preset intensity delivered. As already mentioned, the light fibers are available in different versions. Here you can see the wide angle and then the spotlight fiber. The light fibers differ in terms of their divergent illumination areas. A wide angle guide illuminates a larger area than a spotlight fiber. The light fiber can now be inserted into the trocar. The third and last trocar port is used to accommodate the respective working instrument, in the first step of an intervention in the rear section of the vitrector. The vitrector has been removed from the sterile outer packaging and should now be carefully removed parallel to the blister so as not to endanger the sensitive cutting tube. The tubing system of the vitrector has two connections. The color red stands for the aspiration and the color blue for the compressed air. There is also a hose separator that serves to shorten the aspiration line if necessary. And finally, the vitrector itself. The handpiece is coated blue. In this case, it is a 25-gauge vitrector. The red safety connector is to be connected to the corresponding counterpart on the cassette. The blue connection is connected to the device system and directs the compressed air to the vitrector, which realizes the movement of the cutting inner tube. The compressed air causes the forward movement and the internal spring causes the backward movement. The cutter shown here is a Mach 2 vitrector, which means there are two cutting edges on the cutting tube. Furthermore, this type of vitrector has a permanently open cutting window, which guarantees a constant and high flow. Due to the design features, the set and displayed cutting rate must be multiplied by a factor of 2. The vitrector is now connected to the device system accordingly. The red connector is connected to the cassette, the blue connection is connected to socket 2 below the screen. Here is the side view of the Megatron S4HPS, with the cassette already inserted. The corresponding aspiration tube of the cutter is connected to the red safety connector. Connection socket 2 is similarly illuminated to support socket 1 as soon as the corresponding surgical step has been selected. After successful connection, the vitrector is ready for use and can be introduced into the eye via the previously unoccupied trocar port after the function test has been carried out. You can now see the surgeon's view of the operating field. On the left, the light guide that illuminates the surgical area. Next to it on the right is the vitrector. The vitreous body is a transparent gel-like mass consisting of 98% water and 1% each of hyaluronic acid and collagen fibers. In order to be able to clearly show the process of the vitrectomy, this video was explicitly chosen. This is an asteroid hyalosis, a degenerative phenomenon in which small milky white opacities form in the vitreous. With this indication, the vitreous body is better represented. It can be clearly seen how vitreous body strands are aspirated and cut and how the removal of the vitreous body progresses. Special indications for posterior segment surgery require the use of an endolaser. The laser probe, like the vitrector, should be carefully removed from the packaging so as not to endanger the sensitive instrument. It should be noted that there is still a protective cap on the plug that must be removed immediately before use. The portfolio of GEUDER also includes handles that contain both laser and light fibers in order to combine two functions in one handpiece. To connect to the Endotron 532, the protective cap must first be removed. The plug is inserted into the socket and the thread is turned clockwise until the symbol above it lights up, indicating that the laser fiber has been successfully connected. The Endotron 532 is connected to the Megatron S4HPS device system via a data cable and can be operated via its GUI. In the user interface, switch to the surgical step in which the laser was programmed accordingly as a function module. When the laser is activated, an information window first appears in the S4HPS, which draws attention to the fact that a laser safety filter must be used, which can either be swiveled in or permanently installed in the microscope. Settings such as laser power, pulse and pause duration and the intensity of the pilot beam can be made on the user interface of the device system. The laser function can also be activated via the GUI and triggered via the system foot switch. For regulatory reasons, the foot switch must be equipped with a laser protection bracket if it is possible to control a laser device in order to prevent accidental triggering. If the laser device is activated or in standby mode, the so-called pilot beam can be seen, which is harmless to the human eye due to its wavelength. It serves to localize the area of the subsequent laser beam application. In this situation we can see the laser, which in this case is emitted in a pulsating manner. When the laser is not active, the red pilot beam can be seen, showing where the laser beam will hit. For laser applications, everyone present in the operating room must wear laser safety goggles, and in many facilities a sign is activated in front of the operating room, indicating that the room may not be entered as long as the laser is active. Finally, we look at the oil injection system, which consists of a connection hose with a connector to the device system and a screw cap for a safety cartridge that is also included. A VFI cannula can also be used with the oil injection system. The plastic element is first removed from the silicone oil syringe, then the syringe, taking into account its wings, is inserted into the safety cartridge. The screw cap of the tubing system is then placed on the cartridge and screwed on with slight pressure by turning it clockwise. As soon as a click can be heard, the locking has taken place and can no longer be released. After removing the rubber stopper of the silicone oil syringe, a VFI cannula can be attached. VFI stands for vitreous fluid injection, whereby the silicone oil removal is referred to as VFE, vitreous fluid extraction. Finally, the tubing system is to be connected to the bayonet lock port 4 of the device system. Here, too, an audible click must be ensured in order to guarantee correct connection. The pressure with which the oil is injected into the eye can be set in the correspondingly programmed surgical step of the device's GUI. There are silicone oils of different viscosities, with a 2000 oil being less viscous than a 5000 oil. Furthermore, the Megatron S4HPS already offers presettings for pressure values for the use of 1000 and 2000 oils. This video shows the entry of silicone oil into the eye. On the left in the picture is a backflush instrument that implements the aspiration. The eye is now completely filled with silicone oil and the intraocular pressure is checked tactily in order to make any necessary corrections. If silicone oil is put into the air-filled eye, the Megatron S4HPS guarantees constant compliance with the preselected pressure value of the air injection. Pressure peaks caused by the oil input will be compensated. This brings us to the end of the instructional video, in which you were given an overview of the necessary device systems and corresponding accessories. We provide further information regarding parameterization or interventions in the anterior segment in other application videos.